In this lecture, we are moving towards a new topic, which is curve fitting and interpolation. And we will look at how we can do the curve fitting and interpolation of, you can say, the different interpolation of the function at different values, interpolation of the data at different values using the numerical analysis and computation. So what is basically the curve fitting and the interpolation? So if I talk about, you can say, the general form, you can read this one. The curve fitting is a procedure where a function is used to a given set of data in the best possible manner without having to match the data exactly. So for example, let's say this data is given to us. Alright, so we can use a function or draw a line that best matches or best crosses that data. Alright, so it may not cross all the points to be exactly, but it is the best possible solution or best possible, you can say, the function that can pass through all the data points. So it is a best possible manner and best possible approach that can best, you can say, match the data exactly. So this is what is a curve fitting is basically. So why do we need that? Similarly, the interpolation is basically, for example, you know that in this example I have just drawn, these were the data points. Alright, so basically these were the data points. So I think one was here also. So these were the data points. So you know that only at these points we know the exact value. For example, if we want to know what is the value at this point, alright, so we can only find it by, you can say, this is what we call the interpolation of data. So this value is not given to us, but we interpolate the data to find the function value or the data value at this point. So this is basically what is interpolation. So why basically we study curve fitting and interpolation? A set of data may emanate from various sources, from conducting experiments involving measurements of physical quantities. So all forms of data can come in the different formats. So we could get the different data. We may need to find the best possible function. We may need to look at the different trends, if it is moving and what kind of relation it is having. Maybe it has a linear relation, or it has a quadratic equation, or it has other polynomial, you can say, relation. So we need to look at what kind of behavior our, you can say, the data is explaining or data is showing. An available set of data can be used for different purposes. In some cases, the data is represented by a function. So in some cases, we need to use a function to represent our data. Such a function may be obtained through curve fitting or approximation of the data. So basically the curve fitting method is basically used if we need a function, or we can also use the curve fitting for the interpolation purposes also. Interpolation we already discussed is basically interpolating the values at the different points which originally are not given to us. As a result, while the function does not necessarily yield the exact value, so the function, it does not yield the exact value at all the data points, but it is, you can say, the best possible we have already discussed. Several types of functions and polynomials of different degree can be used for the curve fitting process. Alright, so for example, this looks to be a quadratic, you can say, line or quadratic function that I just used in the green line. So it could be a spline, it could be a straight line. So different kinds of you can say the polynomial relations could be used in the curve fitting process. So for example, this is, you can say, a single function that is fitting all the points exactly. The aforementioned function or polynomial can then be used for the interpolation purposes. This is to find the estimates of the values at intermediate points. Right? So interpolation is basically is the process to find the estimates of the values at the intermediate points between the given data points where the data is not available. So for example, at this point we want to find the value at this point, so we cannot find the value until we have that you can say that function which can give us what would be the data based on the previous or next values. So interpolation is basically finding the data at intermediate points where it is not available. For example, here or here, we can find the data using the interpolation method. So one of the basic, or you can say the most easiest one of the regression is basically, it is called the linear regression. It is the simplest one, and this is, you can say, the equation of the straight line. So the equation of straight line includes two variables only, a1, two constants only, sorry, a1 and a2, a1 and a naught. The best fit of a set of n data points x1 y1 to xn yn. So for example, this is x1 y1, there are 1 2 3 4, and so let's say the n data points, and the best fit to all these data points will be, you can say, some line that can you can say must be closer to the most of the data or data points on the chart or on the graph or on the data set. There are two coefficients a and a naught whose value is needed to be determined. So this is basically the line equation. I think all of you must be familiar with this equation, that basically a straight line can be represented using this general form where a1 and a naught basically can differ. So the data first needs to be plotted, then see whether the independent and dependent variables exhibit a somewhat linear relationship. If this is the case, then the coefficients a and a naught are determined such that the error associated with the line is minimized. So first we can do is we can plot the data and see if there is some kind of you can say a linear relation available. So for example, if this kind of a pattern is available, so we can say come into, you can say, a result that linear line or linear interpolation could work between these points. Whereas if the data point is let's say the data points is like maybe this one, so maybe we come to the point that this may not give us, you can say, the exact value. So maybe some quadratic or spline functions could be the best possible scenario in this. So in this case, so basically the first thing we need to do is maybe plot our data and see whether it will give us the linear relationship or not. If it gives us the linear relationship, so we can, if we come to the understanding that the linear regression will work, then we can come towards the next step, which includes to find the values of a1 and a naught. So at each data point xi and yi, the error ei is defined as the difference between the true value yi and the approximate value a1 xi plus a naught. Alright, so this is if you can say the original line which will you can say the best fit the data will be the line that will be you can say which can reduce the individual errors between these points. So what is basically the error? For example, this point y1 x1 x1 y1 here lies, and this is, you can say, the points of the corresponding point of the line. So basically this e1 represents the error here, so it is equal to y1 minus that corresponding point on the you can say line, which is basically shown to be the same as this equation. So there will be corresponding a1 x value and a naught value. So this represents the individual error. All right, so because the line is basically, this is the y value of the line at any point. All right, so So basically error is equal to the y value of the data point minus the y value of the function. Alright, so y value of the function is basically we are giving it with this equation. Alright, so if we replace this here, so this is basically the individual error of all the points, and we can come out to be. So for example, here E2 is maybe less, E1 is more. Similarly, this one is positive error, and this one is maybe E, and here is negative error. So these are basically all the errors here. So these individual errors will be used to calculate the total error associated with the line. So this is our line. So all of these errors will sum up to give us the total error. Different strategies can be considered for determining the best linear, you can say, set of n data points. So there are different strategies to, you can say, consider the error of the term. So one thing is, I think, already clear here, that our main goal in terms of linear regression is to minimize the error. So to draw a line which is more closer to all the data points and results in the less error. So what are these strategies? One strategy is to minimize the sum of all the individual errors. So one strategy is that we want to minimize E1, E2, E3, and E4, and we can write this one as it is the sum of I is equal to n, and if n is the number of data points. For example, we have n data points, n values, so we sum all of these errors. So this is the E individual error. We sum all the individual errors, which is equal to this. So this is one way. So, but there is, you can say, one side effect, or you can say the one downside of this method is that this E1 is basically a positive error, and this E3 is basically a negative error. So this E1 and E3 could cancel out in this summation. Alright. So it will show us that our error is less, but the error will still remain there. Alright, so this is, you can say, one drawback of using this kind of approach. So it will you can say the positive and negative errors will, you can say, cancel each other out, but you can say the difference of our line with these individual errors will be quite more. So this does not will give us, you can say, the maximum or the best possible solution. So then there is a side, you can say, the downside of using this approach. So in order to minimize the sum of, you can say, in order to minimize the error value, which I just mentioned, that the positive and negative values could cancel each other out. In order to come up with this, you can say, with the solution to this problem, is one way we can do it is we can use the absolute errors. All right, so we are considering this one to be positive, and also the negative errors we are considering to be positive. So we are taking the absolute norm of our all errors, and then we are adding it together. So in this way we can come up with the, you can say, one value of the E value. So but this approach also can give us, you can say, the different lines. For example, this line could give, you can say, could give us the E value. Similarly, there could be also, if the line is drawn maybe like this, it could also give the same E value. All right, so this means that in this approach there is not a unique solution. All right, so there could be not one best possible, you can say, the line you can draw. So it can give you multiple options also. So in order to differentiate between that options is also a difficult task. So that's why we come up towards the third strategy, which is to minimize the sum of the squares of all the individual errors. So what we do here is basically we take all the individual errors and we square it up. Right? So we take all the individual errors and we square them up and then add them together. So what it do is the bigger errors, for example, you can say the 9 square will be very much more than the 3 square. All right. So if the errors which will be greater will be, you can say, contributing more than the errors which will be less. So in this way we will be, you can say, moving towards a very unique solution, a very unique form that will minimize our error. So this approach is basically the best approach to solve this kind of a case. So this criterion to find the line of y is equal to a1 x plus a naught, that the best fit the data is to determine the coefficient. So this is, you can say, the best fit we can get using the scaling approach here. So but the problem now is to find how to find the values of a1 and a naught. So this is the error relationship we finalized after you can say selecting from the different approaches. So we can find the values of the a naught and a1 by finding their minimum. So we can take the partial e over partial a naught. No? So similarly, partial e over partial a naught, we can put both of them equal to 0 to find the values of a1 and a0. So for example, if we do partial e over partial a naught, so you can see that this is a naught square, so it will become, and there is a minus sign also, so it will become minus 2 a naught. Alright, so it is a naught square and it will become minus 2 a naught. So we can bring this minus 2 you can say at this place before the summation, because it is a constant quantity and all of the other expression remains the same. So if we move this minus 2 towards you can say the right hand side, we can get this equation. Similarly, when we apply partial e over partial a naught, we can get this relationship, because this is you can say a1 square and xi square. So xi square is basically a constant here, whereas ai square will become 2a1. So this minus 2 is basically, this minus is because of this minus here. So this minus 2 can come outside. Alright. So this x1 square can be, you can say, in order to keep the same format, we have x1 here, and we can get it out also. So you can basically solve this relation, or solve this this partial derivative by yourself. Maybe I am having some, so maybe it is best you can say uh, best way is to, you can say, open it out and then solve this expression. So when we will do that, it will give us this expression, because minus 2 will move to the other side and will be equal to 0. So these are the two equations we will get after taking the partial derivatives. Alright, so after expanding and rearranging the equations, it will give us these two simultaneous equations. So how we are getting that is, you can see here that if I multiply this summation inside, so this one will become, because this is n, so this one will definitely, a naught will become n, and this equation will become summation I is equal to 1 to n and yi. Alright. Similarly, this one will become, so this is basically what is represented by here. So this is basically n a naught. So if we multiply this summation inside of this equation, we will get this first equation. And similarly, if we multiply this summation inside of this equation, we will get this second equation. So what this equation is representing is, you can see we have n multiplying by a naught and a1. So both these equations are in the terms of a naught and a1. All right, so it is just like the simultaneous equation where we have one matrix A and we have one matrix X, and which is equal to one matrix which is B. So this is basically in the similar approach to that. So we can solve this simultaneous equation to get the values of a naught and a1. How we can do that is, you can say there are different methods of doing that. One of the easiest ones for here is using the Cramer's rule. So I have just mentioned here, you can say the hint towards the Cramer rule. So how you can solve them. So if we have ax plus by is equal to e and cx plus ty is equal to f, these two equations, then the x value, which is the first one, the x is basically, you can say, representing a naught here. The x value is basically can be found by taking two determinants in the numerator and denominator. So it is equal to, so a naught here will be equal to e minus t, e minus d. So e here is this. So you can see this yi multiplied by d. D is basically this value. So this represents e multiplied by d minus f multiplied by b. So what is f is this value. So this is f multiplied by b. So b is basically this value. This is b xi. So this is b. Alright, so we are just putting the values here of all the you can say constant. We are solving this equation using these formulas to get these two, you can say, answers for the a1 and a2. All of this is similar. All you need to do is you need to make sure that you are solving it correctly. That is, the upper side will become ed minus fb. Alright, so this one is basically ed minus fb, this. And similarly, in the lower side, you will get ad minus cb. So this is basically ad minus cb. So similarly, for the a1 is basically represented here by 1. So a1 can be found by a multiplied by f and c minus c e. So this is af and this is ce. So these are the two formulas that we get after applying the Cramer's rule to the equation. And these are, you can say, what we want to know, because we only have to find a naught and a1 value. So we have found it by solving these two equations using the Cramer's rule. So now we come towards an example. So we have this in these data sets. Consider the table data in the table. Using least square regression, find the straight line that best fits the data. So there are 6 data points, so n is equal to 6. So you can see here is there are different summations that we need to find. For example, we need to find sum of all the x values. Alright, so we can find the sum of all the x values. Sum of all the x values is, these are the x values, 0.2, 0.4, 0.6, 0.8. So if we sum all of them, we can get 4.2. Similarly, the other sums include sum of all the y values, sum of xi and yi, and sum of xi squares also. So we have calculated all the sums of yi. Sum of all the yi is basically all of these quantities sum, which is 51.2. Similarly, xi square is 0.2 square, 0.4 square, 0.6 square, similarly to 1.2 square. So we will calculate this also. Similarly, xi yi is basically x multiplied by y. Similarly, x multiplied by y. So we can get the sum of this quantity also. After having all the summation values, we can put in our formulas for A1 and A naught. After putting these formulas, we can get the value of A naught and A1. So these are all the values we calculated in the previous slide, and we are putting these values in the equation here. So as we have found the values of A1 to be 0.5429 and A naught to be this, we can put in our general form the equation. It was A1x, y is equal to A1x, y is equal to A1x plus A naught. So this was our general form, and we can put the values we found at these points, and this is basically the graph which shows all the data points. These are all the data points which we use to find the values of a1 and x, and you can see that this is the linear regression, this is the equation, this is the function of the, this is the equation of the line we just calculated, and it is, you can say, passing through the data in the best fit manner, in the best you can say possible manner. So this is how we use linear least square regression. So the word linear here represents because we are using the linear equation, and the least squares represents here the square, least square represents you can say the squaring of the error terms we did in our formulation of the total error. So this is how we apply and how we use the linear least square regression in finding you can say the curve fitting process, in finding the best curve and finding the best, you can say, the line fit of the given data.